electron diffraction, and so you do the same thing. You put in the mass of the electron into here, and you calculate what this factor is, and it turns out to be 12, roughly 12, and you obtain, in order to have the electron matter wave to be about 1 angstrom, you need an electron kinetic energy of about 144 volts. So, so in electron diffractometer, electron the so-called low energy electron diffraction, you need about 100 to 200 volts in order to see diffraction phenomena and see your lattice inside your bulk and on the surface. Okay, and we are going to talk quite a lot about this electron diffraction later on after we discuss surface structure in this, because indeed this is the primary tool to probe the structure of the surface, just like X-ray diffraction as the primary tool to probe your bulk material, both for standard material science and increasingly for nanosciences as well, because the X-ray technology has improved to the point that you can detect very small volume of material. And finally, you can also do helium beam. You can create. It's not such an easy thing to create a neutral electron beam, just like neutron. Neutron is neutral. Electron is easier because it's a charge, so you can create a electron beam. Because we know how to create electron beam, because all the old televisions, careful ray tubes are done with electron beam. So we know how to manipulate, and you just need to have voltages in your electrode to move to direct your electron beam. But neutron or helium atoms, it's much more difficult because you don't have a charge. They are neutral beam, so it's very difficult to control the direction of the beam. Okay, so they are a little bit more difficult experiment in terms of doing this. So, but it is possible, and people have done it for a while. And helium atom scattering has gone down since because it's difficulty. Both of these, helium atom scattering and neutron scattering, has the use of these techniques has been reduced quite substantially in recent years, simply because to create a neutron beam is very difficult, and also to create a helium atom beam is also quite difficult. At Waterloo, before I came, there is a professor by the name of Giorgio Scolas, and he did a lot of work using helium atom scattering, and his work was to probe structure as well as surface phenomena using helium beam. So helium scattering is same thing. You can work out the matter wave for helium. You now substitute the mass of the helium into m here, and it works out to be about 0.14, and then you got about this. You got about 20 millivolts. So usually when you talk about helium scattering, you're talking about thermal energy, right? The 20 millivolts is more like thermal energy of your helium beam. So oftentimes when you do helium scattering, it's very difficult, not because you need to cool your sample down. Otherwise, your helium beam, if you have one object around your helium beam, you warm up your helium beam, and then you no longer have diffraction phenomena anymore. Okay, so that's why it's so tricky to do, and it's a very difficult experiment. Electron diffraction, very simple. X-ray diffraction, very simple. And these two remain to be very popular technique today. Okay, so let me just very briefly, since people, probably some of you have worked with materials, you probably be aware of X-ray diffraction. As I say, there is a course on X-ray diffraction on the Waterloo side, I think, that discuss in great detail about how the diffraction and other things. But in general, very quickly, what X-ray diffraction is very simple. Is that you have the Laurie method by the name a German scientist, Max Laurie, who discovered that how to do the diffraction from crystal. So you fix the crystal, you change the wavelength of your X-ray, and you see spot and so-called Lorentz pattern, and you vary the wavelength from 0.2 to 2 angstrom, and then you see the change in the pattern of the X-ray spot, and from there you can work out what is the structure inside your powder. And of course, for this is the foundation of X-ray diffraction. I think he got Physics Nobel Prize in 1918 or something like this. Can't remember exactly, but he did get his Nobel Prize because of this technique. And then we have rotation crystal method. Is that you, instead of fixing your crystal, you hold your crystal into place and you rotate your crystal in any orientation, and then you fix your lambda. So you have the wavelength of your X-ray is same, and then you rotate your crystal. And this leads to the so-called high resolution X-ray diffraction, or sometimes called four-circle X-ray diffractions, because you can manipulate the orientation of your crystal that you have. In the Lorentz pattern, you fix the crystal in space, and you essentially change the wavelength to see how this pattern changes. And this particularly is very powerful for if you have very tiny amount of crystal, right? So let's say you have a protein crystal. Protein is usually very hard to make a big crystal of. If you have a tiny amount, you can do this. You can just fix it in your gyrometer, hold it in space, and then you just zap it with your X-ray and take picture essentially. And the department, I believe the department has something called Lorentz camera in our X-ray facility. So all they do is that they send in different wavelength, and then they take a picture of this pattern, three-dimensional pattern. At Wall Lab, we have this rotating crystal method, which is a four-circle. Sometimes it's called four-circle, because you have four different circles rotating your sample and your X-ray source and your detector, essentially detector. And then finally, I think most people are very familiar with. So here you have a fixed light source with a fixed wavelength. Maybe usually it's copper source, because the copper give you about, it's a 40 kilovolt, give you roughly 1.5 angstrom type radiation, and it's quite appropriate for your scattering. So all you have to do is just rotate your crystal to expose the different plane to your light, so that you can generate different scattering phenomena, diffraction pattern on your screen. And here you finally have this powder diffractometer. Everybody knows about powder because instead of single crystal, so this is usually a single crystal type method, whereas the powder is that you have multiple crystal in powder form. It means that you have a bunch of crystal, powder is crystal, randomized in space, right? So therefore, you don't really need to rotate your crystal. Here you have a single crystal. Here you have multiple crystal merged together in different space. So here you just need to send in a photon and then see how it diffract, because all the plane you would expose, you will see all the plane because of all the orientation of your powder in your sample. Okay, and every chemistry department, I'm sure, has powder diffractometer. It's an extremely powerful tool for material science. If you are making powder, right, you just have to put your powder inside, and you get all the orientation